The speed of a wave on a string depends on two things: the tension in the string and then also the mass per unit length. So the mass per unit length, for that we use the symbol mu. Unfortunately, we've now introduced so many things that we're starting to recycle symbols. So this is not the coefficient of friction, but is now in this context the mass of the string divided by the length of the string, and has units of kilograms per meter. So a heavier string means that waves will travel more slowly. And if the string is very tight, the restoring force is stronger, the tension is higher, and the wave will propagate more quickly. Superposition is what happens when you have multiple waves on the same string or in the same material. When this happens, the two separate waves will add together. So you can see a cartoon here of two waves approaching. As they run into each other, they just combine to form a single wave and then pass through each other and continue each on their own separate way. Down here is a cartoon animation of the same sort of thing happening. We have two waves, they approach together. When they overlap, they combine, they add together, and then they pass through each other and each continue on their own separate way. If you have continuous waves, so waves that are ongoing, the way they add together can form a superposition of the two waves. Now, if you have two waves that are in phase, that means they are doing the same thing at the same place at the same time. So here we have two waves and they're kind of going along together. They each have a peak in the same place and they each have a trough in the same place. These two waves will add together constructively. So that means if you add these two together, they just make the same wave with an even bigger amplitude, an amplitude equal to the sum of the two waves that you're adding together. If, on the other hand, the two waves are 180 degrees out of phase, so that means the peaks of one wave match up with the troughs of the other, then these two waves, when you add them together, will perfectly cancel out. You will get destructive interference, and you will get a flat string or a flat material that doesn't look like it has waves on it at all, even though it actually does. You still have the same amount of wave energy passing through this material, it's just that the waves themselves have canceled out. Now, waves can reflect off the end of a material, and the way that happens depends on if the end is fixed or not. So if you have a wave coming along a string and the end is fixed, the wave will invert when it reflects off that fixed end. On the other hand, if the end is free to move, then the wave is not inverted, but goes back having the same sign as it did when it was coming in. Next, let's take a look at this example problem. If we triple the mass per unit length of a guitar string, how will that result in changing the wave speed? So what we're doing is we are tripling the mass per unit length. That means that the final mass per length is going to be equal to 3 times the initial mass per unit length, where we use the symbol mu to designate mass per length. So we know that the wave speed, and this is the wave speed initial, will be equal to the square root of the tension divided by the initial mass per unit length. If we look at the same thing for the final speed, the final wave speed would be equal to the square root of the tension over the final mass per unit length. However, we know that the final mass per unit length is 3 times the initial mass per unit length. And we know that we can rewrite this expression as being equal to the square root of 1/3 times the square root of t over the initial mass per unit length. And so this square root of the tension over the initial mass per unit length, this is just equal to the initial wave speed. So we've found that the final wave speed is equal to the square root of 1/3. Well, the square root of 1 is 1, so that's the same as 1 over the square root of 3 times the initial wave speed. So it changes the wave speed by a factor of 1 over the square root of 3. So here is another question. Let's say you want to double the speed of a wave on a string. How should you increase the tension of the string?